So I said I've been interested in this subject for many years, and it's a gripping subject because it's universal. You can talk about true mathematical writing, you can talk about mathematics, you can talk about various aspects of mathematical education, you can talk about secondary school education, you can talk about British class system, you can talk about the forever ambivalent relationship with Europe, you can talk about government cuts, you can talk about everything. You know, you could construct a portrait of Britain starting from mathematical writing. Now, I only have half an hour, so I will talk mostly about a second-year course in mathematical writing at the University of London, but you will see that it is just impossible to deal with this subject in isolation. So, why mathematical writing? This is how I present the course to the students, second-year students. They have a choice, so they can, it's the first time that they have a choice in the second year, so that they can choose whether to do this course or not. And so I tell them there are 3 reasons for it. The third reason is that writing is an essential skill, and many students are not good at it. British employers complain about lack of literacy among the workforce, and you can bet that one will charge the student £9,000 that this topic would become red hot. The academic reason for this course is another one, is to prepare for a final year project, or as an alternative to. The percentage of students that do a project in the final year is too low. It's probably embarrassingly low, particularly if you compare with certain European system where every graduate in mathematics will have to do a project with a presentation. The problem is that many students are not ready for a project in the final year. And so what we want to do is to create an alternative for the students, something a bit less challenging. And for us, something a bit less demanding from the viewpoint of the resources. But of course, the main reason is that writing helps you think. And if you learn how to think, then you will know how to do a final year project, then you will learn how to write well, and then you get a good job, etc., etc. So this is the real reason that I'm interested in. There is also another reason, which I don't tell the students, is that it's the ultimate reality check for a teacher. Writing, or watching students write, rather, gives you X-rays into the student's mental processes. Basically, there is no hiding place anymore. At Queen Mary, there is an initiative called Thinking Writing, which is a gathering of people interested in writing from all kinds of corners of the university, and it's amazing the convergence of educational ideas that just originate from the common interest in writing, and also the distaste for cover-up or hypocrisy or anything. It's really if there is any shortcoming in the education that you provide the students don't achieve what you think or claim they will achieve, well, it become instantly clear in the moment in which you ask them to write. So there is a nice little booklet called Ideas from Mathematical Education, where there was a nice passage at the beginning that illustrates some of these things, and they said that we find it illuminating to ask students to think aloud as they work on mathematical tasks. This often uncovers fragility in the knowledge of even the strongest students. So this idea that the act of communication, it's really very important because it allows you to see what goes on underneath. And somewhat along the similar lines, a Queen Mary mathematical writing student commented on the unexpected depth required of their thinking when asked to offer verbal explanation. Now, these sort of things should really surprise no one, because a professional mathematician knows the absolute central importance of communication. If you want to learn a subject, the best thing to do is to teach it. If you think you've got a theorem, well, write it out. Then you will know whether you have a theorem or half a theorem. There is nothing like giving a talk as a moment for achieving a synthesis of a certain subject. But for some reason, the students are exempted, and this, of course, links up to what Kevin was saying. You know, that we try to do a process of reverse engineering and to decode this fragmented signal, to try to reconstruct the process, the mental process of the student, instead of simply asking them to explain to us what they do. So let me give you an example of this unexpected depth. So this is also how another aspect that I present to the students. This would be let's say, the ideal outcome of a successful student, for a successful student in mathematical writing. So you have this problem. On the plane, I have a circle and a point outside it, and I must find the lines through this point which are tangent to the circle. What shall I do? The mathematics is secondary school mathematics, or perhaps first semester of university mathematics if we want to do some remedial geometry teaching on conic sections. But there is no more than that. And then I ask the student to answer this question over the phone. Don't be distracted by formula or anything like this. I just want to know what to do. Just give me the instructions. Now, if you start thinking about this thing, then you realize that this task, first of all, requires understanding of the structure, and require a lot of organization. It will give the students an opportunity to express their knowledge, intelligence, and individuality. I stress on the individuality. The students really need to develop their own voice. And there's nothing like a deregulated space. Give them some kind of non-prescriptive task to allow them to develop this voice. But of course, this is the reality check that I was discussing. You will also expose immaturity, logical fault, incompetence, etc., etc. So let me show you what could be a solution to this question. Well, I've written it in 4 paragraphs. It's about 150 words or so long. So write down the equation of a line, and this equation will depend on one parameter, the line slope, which is a quantity to be determined. Now, of course, here you spot some specialized language, parameter. There are going to be variables and parameters, and in mathematical writing they're used for different purposes, and it's important that you differentiate this at this stage. Then we have to put together the equation of the line and the equation of the circle and form a system of equations, and then after a substitution you end up with a quadratic equation in one unknown. There is another point of very great structural importance, which is a kind of grown-up point, the fact that they have an equation whose coefficients depend on a parameter. This is very much the unexpected depth that you wouldn't quite think it would come out of this rather elementary problem. Then you have to equate the discriminant of the quadratic equation to 0 to obtain a desired equation. There's a technical term, discriminant. They should all know what it is. It's just quadratic equation, but you'll be surprised if you ask them to explain to you what is the discriminant, how many of them don't know how to do it. And then there is a fine point that the equation, the discriminant equation is also quadratic. It has to give you 2 solutions. And then you wrap things up and you start connecting the information that comes from this discriminant to the geometry. And then there is a little fine touch at the end. You know, mathematicians should think like mathematicians. They should see all the things that can go wrong, and if you have lines that are vertical, have infinite slope, so you will have to do a separate treatment. So if a student will give you this, then you would know that this is a first-class student. End of the story. And all the mathematics, I mean, this is a secondary school mathematics. So there is a lot of unexpected depth, and this is what I knew all along. But I'm glad that the students have found that. So, but this is the dream, right? So now let's crash land on reality. This is what happens. This is an experience that happens to all of us all the time. So we try to teach some university mathematics to the students. We start off with the definitions, and then we state theorems, and these are just a beam of neutrinos for the students. It's an irrelevant piece of information, and most of these things have to be memorized for the exam if the lecturer is obsessed with this stuff. Then we give some examples which are meant to illustrate the definitions or the working of the theorems, and the students instantly latch onto the example, and for them they are hardwired to the assessment. At this point the teacher has a different idea about the assessment, and you get this sort of lack of communication between 2 different approaches. So the students will undo all your carefully planned schemes under your own nose. It will turn things upside down, but this is not just the contrast between two different forms of learning. Is that this example-based form of learning is really extremely damaging. It causes students to underperform, to underachieve with respect to their abilities. And this is it's actually a disease that reaches level of epidemics, and this is why this problem is so difficult. So let's talk about this disease. The main problem is that many university students don't know how to study. That is the punchline. Recently, a colleague of ours went to a meeting with industry, a major British industry, and he asked them, "What do you want from mathematics graduate?" And the guy said, "We would like them to be able to study," which is interesting, right to the point, coming from an unexpected source. Now, if translating this in the context of mathematical writing, I wish that my students' writing problem were due to language difficulties. We may be really desperate to believe that they're due to language difficulties because they will exempt us somehow. Let me just give you one piece of information that concerns British universities' best kept secret, the Erasmus exchange. So I have every year a small but steady contingent of Erasmus students. They come from Germany, they come from Denmark or Italy. These students are always in the top 25% of the performance region, and more often than not, they are at or very near the top. So these students have a solid preparation in English, so they have a functional English, which is enough to write mathematics. They get a little bit of training in writing mathematics, they improve it, but of course it's a self-selected group of students. They're highly motivated and they're skilled, otherwise they wouldn't be here. And it is that those skills that in the end produce good writing. So why the university students don't know how to study? Let me focus on two things, because I would like to some kind of define what is exactly the problem that we are facing. The first cause is the league table. Right? So I don't know if you've ever seen a teenager preparing for a mathematics A-level exam. Well, I've seen it. Right? No books on their desk. Big pile of past paper, practice, past paper. After a while, if you do this sort of thing, you realize that the question falls into certain categories. They're just some kind of templates. And then you don't even need to read the question anymore. You read the beginning of the question and you know exactly how it's going to end. And so you just have to pick up some data from the question. And of course, I mean, the secondary school are divided into two groups. The school that don't have league table anxiety, they educate people, and as a side effect, the students will do well in this predictable exam. But then there are the schools that do have league table anxieties, and they take care of their own anxiety first, and take care of the education of the students just as a second priority. And so they just train them for exams. And so if you get a student with decent A-level exam, you don't know whether this is a thinking young adult or a machine that's been programmed to pass examination. So it's a bit like the film Blade Runner, right? You just don't know, right? So what is the result of all this? Well, you've seen in the slides before, example, but really what happens is that the concepts are replaced by processes. The role of the teacher is to teach me how to do the things that turn up in the exam. You see, just like teach me how to download the song from an iPod. The inverse of a matrix become the computation of an inverse of a matrix. Cycle decomposition of a permutation becomes the computation of cycle decomposition of permutation, which you can do without knowing what is a permutation, which you can do without knowing what is a cycle, which you can do without knowing how to spell decomposition. The cycle decomposition of permutation belongs firmly to first-year university mathematics. The computation is a trivial pattern matching exercise, infinitely easier than the easiest Sudoku. You could not put it on a Sunday newspaper because you would bore the readers. But of course, now the wheels are under league table anxiety, student satisfaction survey anxiety. Hey, this is great. Let me sprinkle my exam by a few more processes. Let me shrink the concept a little bit. I will achieve the politically correct progression rate that my head of the department is so obsessed about. And shh, don't tell anybody. There's going to be no evidence of it. And so it actually works. It works well. And we're all guilty to some extent to this sort of thing. So this mathematical writing is actually somehow trying to counter this sort of approach. But there is another aspect which is really never discussed enough. And I don't understand why it's not discussed. Where have I learned how to think abstractly? Where have I learned the precision of expression that is needed for mathematical abstraction? Well, you know, I started at age 11 with grammar. Lots and lots and lots of grammar. It's a formal logical system. You have to know what is an adverb. You have to know what is a pronoun. You have to know how to identify them in a sentence. And then you have to have to do the syntactical analysis of a sentence and look at interrelations and functions of various types of a sentence. After that, Latin, lots and lots and lots and lots and lots and lots of Latin. Of course, it's a language, so you have to learn new words. But most of it, Latin is just a massive, protracted exercise in logic. After that, foreign languages, lots and lots and lots and lots and lots of foreign language. It's properly studied. I study English actually with grammar and syntax and all that. If you study German or Russian, it's more or less like studying Latin. They have a similar structure. And then lots and lots and lots and lots and lots of Euclidean geometry, we all have done. And then lots and lots of philosophy, where you learn how to distinguish between, you know, fine difference of meaning. And then also mathematics. Now I look at my students. Grammar. A minority of them are fluent in English grammar. If I say indefinite article, they don't know what I'm talking about, many of them. Latin, or classic in general, virtually nobody has studied that. Euclidean geometry, we all complain about the shrinking of Euclidean geometry in the secondary school. Languages, well, in Britain, let's not deal with that problem. And then philosophy, we get a few students with an A level of philosophy. I much rather having a student with an A level in philosophy rather than the nerdish second A level in further maths. They're kind of better human beings from my perspective. But we get only a handful of those. And so everything rests now on the shoulder of the math teacher. If the math teacher understands exactly the enormous responsibility that they have, fine. But now we go back to the point I raised before. If the math teacher is anxious about league table, then the student had it. And so what happened with these students is that their universe is made of words without exact meaning. And also the symbols that go with the words. So the students understand procedural accuracy. If you tell a student that a wrong sign turns something right into something wrong, then they understand it. But they don't quite understand the demand of the exactness of expression, or thinking like a lawyer, which is what mathematicians do. So what happens if concepts are replaced by processes, and if words don't have exact meaning? That the student can't think abstractly, they can't do proof, they can't write. And often the inability of the students to do proofs is, in my opinion, incorrectly attributed to the inability to do deductive reasoning. It's a lot more basic than that. These students don't have the raw material to do deductive reasoning with. I had in a mathematical writing course, I'll show you in the next slide, we do all kinds of exercises about implications, etc. So I had the following, I had a statement that I had to analyze. Every bounded set of rational numbers is finite. And I have to decide whether it's right or wrong, and write the converse, etc., etc. And so the students say, can I give a model solution, past paper, model solution? All right, so I gave them all this model solution about this thing. And then at the end of this exercise, I ask them, now I want you to write on a piece of paper, what does bounded mean? And then after 2 minutes, I said, how many of you are happy with what they have written? You know, raise your hand. And about 10% of them. So I say, oh, come on, I'm not going to put you on the spot. I am not going to ask you to read out loud. I just want to know whether you're not totally disgusted with what's written in front of you. And 20% of the students raise their hands. So basically these people go through the concept of boundedness, knowing that bounded means that it doesn't go to infinity, which is good enough to do low-level operations. But if you have to prove something, you know, either you negotiate directly or indirectly the two quantifiers that are involved in the definition of boundedness, or you've had it. You will never be able to prove anything. And of course you will never be able to write anything, because you cannot write mathematics with a kind of fuzzy vocabulary. So let me give you an idea of the syllabus of this course, then an idea of the organization, and then I'll give you some examples of the actual teaching material. So the course starts with the essential dictionary, which is, it's about 100 words. They're all mainstream. They're all words that the students, essentially, I mean, 98 out of these 100 the students have seen them already, and they've seen them for a long time. Bear in mind, these are second-year students, so the most of the material of this course, I would say all of it, in some sense, is first-year material. And then we do this very intensive exercise of translating words into symbols and translating symbols into words. And then we start writing, once we got the words right, then we start writing short phrases, and then at the end of this process we start writing short sentences. So it's a bottom-up. At the end of the course, there are going to be 2 paragraphs, which is going to be the most demanding writing assignment. So you know, we really operate at a very atomic level, if you will. Then there is the description of formal mathematical sentences. So the predicate calculus, basic logical operator, the implication sign, etc. We spend a lot of time in implications, you may imagine, and then of course the quantifiers that allow you to make complex mathematical statement. Now, then once we've got these apparatus, then we can revisit familiar construct concerning real functions, which is a familiar terrain, and a very simple concept, like a function being positive or being increasing, and then with a peak of the syllabus being a function being continuous. But we really want the student to be able to know exactly what they're talking about, or rather writing about, when they describe these things. Then there is quite a lot of instruction. Well, they actually start from the beginning of the course about writing effectively, how to choose the notation, some writing techniques, I will tell you a little bit about it, and then what end up being the centerpiece of the examination, which is writing a short summary. I give the student 2 pages of mathematical material. Bear in mind, at the exam there will be students at the end of the second year. I take a big fat calculus book. This is my typical source, semester 1 stuff. I give them 2 pages of this. I remove all the highlights of everything. I just give me 2 barren pages, and I want a title, 2 or 3 possibly engaging bullet points. That would be the first slide of a presentation, and then I want 100 and 150 words description without using any mathematical symbol. And then the last part of the course is more conventional. It's about proof techniques, spotting and correcting bad argument, and it finishes with existence, proof of existence, effective and non-effective, unique existence, and finally how to define things with particular emphasis on listing bad definition, all the things that can go wrong when you define something. The structure, there's a second year course. It's got 60 students at the moment. Every week it's pretty conventional structure. It's got 3 lectures. There is 1 coursework assignment, which for technical reason we had to ask electronic submission. We can discuss, I can tell you about it, because we had to learn a little bit about this stuff. We were afraid of asking the student to submit electronically, but in fact it turns out to be not such a burden. And then there is 1 exercise class where we discuss assignment problem. The assessment is mostly in the final exam. It has a coursework component which is higher than in any other course. It actually been shrinking. Originally this course was designed by Wilfred Hodges as a course in logic, and he had 40% in the coursework, but it was a tiny course with 6 students, so they can do all kinds of marvelous things that we cannot do. And the resources, it's a very high setup cost. Fortunately, Queen Mary, the Thinking, Writing Secondment scheme gave me some money that bought my, we could hire a substitute teacher and I could write this set of lecture notes, which eventually next year are going to be turning into a book published by Springer. But there is a lot of setup cost. What we had to do, we had to set up a training course for postgraduate markers and teaching assistant, which also it's you'll be able to find it starting from my website. It was done by Will Clavering. It had a 50-page instruction document, and because the postgraduate student is just not ready for doing these sort of things. The supervision of marker has to be very rigorous. You really have to let the markers look at the scripts, and then you had to, without marking, then you had to get together, discuss all the possibilities. It's very onerous marking, no more than 4 or 5 script hours. Feedback is everything. And this is really, to connect to what I said, the student have to develop their own voice. You have to start from what they have written and evolve it. You don't compare what they have written with a model solution. So this is why the training of markers is so important. Then, of course, there are teaching assistants in exercise classes, and there is offer of one-to-one help. Now, this course is I mean, we have cuts all over the place. So, I mean, it's really running at the boundary of what is doable at the moment. It costs, in terms of resources, of man hours, a bit less than half of what it would take to supervise 60 projects. But we could do with another 10 or 15 hours a week. Okay, so let me just briefly. How much time do I have?
Half past, should we say?
Oh yeah, sure.
How many credits is it? Is it 15 credits?
It's just a normal course, yes. So this is 40% of the essential dictionary. You will see that essentially, I mean, these are all mainstream words. But they're very difficult to teach because the students will have an idea of being there, done that. And if you actually test them, you'll realize that 80% of the students will not really know what 80% of this word mean. Try your students on say what is the degree of a polynomial. Right? You will see all kinds of wobbling. So, here it's difficult because you would like to say, okay, guys, this is a summary, so we just refresh our memory of what these words mean. But it's not like this. So this is a typical exercise in the early stage of the course. And this goes on and on and on and on and on and on and on. I want the student to describe what they see. You see, this is not a process. There's nothing to do. And I want 2 levels of description. First, I want to know what this thing is in very general term, and then a final description. And so here you have well, unexpected depth. I mean, you can when you start discussing equation, then you can tell them what is the difference between an identity and an equation. It's a very important difference, and with a very nice structural characterization. But what happens in the classroom is that very often students will characterize number 6 as a polynomial, for instance. But obviously, right, the universe is fuzzy, so it's close enough to a polynomial. Now, of course, if you confuse a polynomial with a polynomial equation, then clearly you're not fit to do any abstract mathematics. So somehow you really have to get this thing right before getting the students started on anything. Now, let me give you some details. So this is a mathematical object. It's clear. It's obvious what it is. There is nothing else that you need to know about it. So the symbols here are completely exhaustive. So what are you going to say about this? Well, first of all, we make sure you understand this is a sequence, right? So there are round brackets, and inside stuff separated by commas. So it's a sequence. Then we look at what's inside the sequence, and the last symbol on the right is an ellipsis, so it's got to be an infinite sequence. And then And then we look at what are the things separated by commas and the polynomials. So this is an infinite sequence of polynomials. And the students at this stage begin to learn that if you have to write this formula down, then, and you want to write it, as Kevin said, in sentences, we'll say, let us consider the following infinite sequence of polynomials. You clarify to yourself what this thing is, and you help the reader focusing the attention on important things. And this business of words and symbols, cooperating with each other will be developed very much in the second part of the course. But then what are you going to see, what are you going to say next? And this is really nice because it's a bit like photography. The reality is out there objective for everybody. But if you take a picture, no two people take the same picture because, because you just put the emphasis on certain things. So you don't want to compete with the symbols because as a description of itself, this formula is just perfect. But you can put it into context. And so you can try to teach the students, well, list the possible context. So you could say, all right, this is an infinite sequence of binomials, if that happens to be important. Or it's an infinite sequence of polynomials in one indeterminate. Or it's an infinite sequence of polynomials with integers, or with increasing degree, or with bounded coefficient, or with coefficient of absolute value 1, or with alternating sign of leading coefficient. All of a sudden, this is a little universe in there. And you have to teach the student how to recognize the various things, articulating using an exact language. Now, this is the opposite from words to symbols. The students are taught standard symbolic representation of set, the standard definition, or the Zermelo definition, and then they are given given sets expressed in words, and they have to turn them into symbols. And there's a lot of unexpected depth here. Here I have in example number 9, where I use again the circle and the lines. Well, this is an example of the verbal description of this object. This is an abstract set that the verbal characterization is fantastically concise. If you try to do that in symbols, then you have to go all over the place. So the student begin to understand that certain things are best described in symbols, certain things are best described in words, and in fact most things are best described using a combination of the two. But the kind of work that you have to do to help the student develop these skills of description is quite phenomenal because somehow you have to construct everything from scratch. So the students are not accustomed to conceptual complexity and indeed notational complexity. So you have to, I do a lot of building expressions step by step. So here I got two objects, a square and a sum. And I can combine them into two different ways. I'm going to construct a composite mathematical object, which is like a Russian doll of things inside the other. And so you can have a square of a sum or a sum of squares, and then you can complete this in one way. This is the sum of the square of the reciprocal of rational numbers, or the square of the sum of the element of a rational sequence. It's sort of this process of identifying the outer layer of a composite object, that the students, I realize that they really need a very careful, explicit training about it. There's also another important point. We define sets in words and in symbols, and then we point out to the students that you can specify the type of a set without revealing its precise identity. And we do, as mathematicians, we do that all the time. And I'll give you some examples. And so you have a certain very minimal arsenal of writing techniques to deal with this, like the set of fractions representing a fixed rational number or given rational number, given a few keywords. But the main point here, in like set of divisor of n odd integer, it's of course the difference between the definite and the indefinite article. And now you see that the students' lack of knowledge of grammar is haunting them in the most unexpected of places, 8 years later. And I realize in marking first year scripts that they go all over the place, confusing the determinate and the indeterminate article. Of course, when you turn that into mathematics, it makes a difference between something being right or being wrong. You if you change one article into the other, you change a mathematical object into another. And as a final point, let me describe something about the description of functions. If you ask anybody to describe these things, they will say, well, you know, this is sort of, it wiggles down and it flattens out. Now, what do you expect a university graduate in mathematics to say here? This is an exercise, is a sort of how to prepare the students for modeling. If you want to model something, then you have to know what that thing is, right? And so the idea here is to have the student describing this object using the specialized terms that we have developed. There's quite a lot in this case. And then at the end, the students are asked to produce a function that looks like that. And so first you concentrate on the properties of the function that involve exact language, and then you try to turn that into a specific representation. Okay, so in the closing remarks, well, I regard writing to be essential to learning, and it's really a question of raising expectations. In Kevin's talk, it was obvious that he has high expectations of the student, and I mean, without that, you don't get anywhere, basically. So the student should really be expected to write more, to write well, and should be expected to explain what they do. I find it is very easy to motivate the student to do this. I tell them, when you graduate, you will have to compete with currently 70 other people for the graduate job. And most of them, unfortunately, will also have a 2-1. What is your plan to get to the top? And so you start telling them about spelling mistakes. Put yourself in the shoes of the selector. They want to get rid of 90% of these applications. If you make a couple of spelling mistakes, well, this guy is going to make me look stupid with my customer. And then if you see an uncertain sentence and you see a perfect sentence, you Google it. And you discover that it's being cut and pasted from Wikipedia, and the application goes again in the basket. When you tell the student this thing, they may not like what you're telling them, but they know that you are talking on their behalf. They're telling something that is very relevant for them. So it is easy to raise expectation. I would say it's easier to raise expectation with the students than among colleagues, as far as I'm concerned. And then I would say a writing course is not enough. A collective effort is needed very much. I would very much like to have 4 or 5 Kevins in my first year, right? In our first year, that would prepare the student for a mathematical writing course. Essentially, as the way we have set it up at the moment, there is just too much on this course, too much. And then I would like just to point out that certain problems cannot be solved. We cannot solve this problem ourselves. It will certainly need some change in secondary school, but also level of universities. I realize that department cannot quite deal with this problem by themselves. Let me just give you two pieces of information which appeared in a conference about writing in the United States, actually. It was organized at Queen Mary, and there is the writing in the discipline approach that's about 20 years old, and it affects Ivy League universities. At Cornell, they have 20,000 students, and they have 190 courses for beginning university students, small groups, less than 20, in writing. 40 of them for the science faculty. At MIT, a few years back, they asked graduates in mid-career to tell what was the thing that they liked the most, and that the MIT provided in their education, and which were the parts that were more deficient. And everybody pointed out that they were not taught how to write. And MIT invested $1 million for a startup scheme. So this is not cheap stuff, and I don't think that can be solved entirely within departments. But it is, I think it is our job to raise the awareness of these things on on a broader stage. Thanks for your attention.
Any questions?
So I was interested that Kevin mentioned that he couldn't do much in the second and third year because the PhD students do the marking, but you have trained PhD students. So once those who've been on your training course, do they mark to your satisfaction?
Yeah, provided that they need some supervision, right? You have to keep an eye on it. You cannot, I mean, you have to periodically check.
Yeah.
But I have never had any disaster.
Are the students who do this course identifiably different in their third year from the ones who haven't done it? Have you looked at that?
No, we haven't done any comparison. I mean, this course is really, I really have in mind the parallel analysis course, and try to create a synergy between the two courses. So I would hope that it reinforces several things the analysis course does, and also try to somehow to prepare the student for the abstract algebra course at the end of second year. But we haven't done any actual comparison as such. It's a course that splits the student, so I get it's a kind of love-hate. I even saw graffitis about mathematical writing. So the student love it, and the student hate it, because it will expose you know, they have to raise to a challenge. They have to be ready to be provoked, right? And they say, okay, this is going to be hard, but the benefits are going to be great. Now, I've seen students of a clear mind hampered by language difficulties. So, and I've seen students, I mean, it was one of the greatest satisfactions I've ever had as a teacher, kind of flourishing in 3 months. I start telling them for the first time, look, spelling mistake is bad. And then correcting the sentences. Then you see, after 3 months, in a very short period of time, you know, bright students that can really do a fantastic progress. But at the weakest end, it's not so rosy, because you tend to get a bimodal distribution. It's irreducibly conceptual. There are no tricks that you can play. You know, you see what you get. And for that reason, it requires a lot of preparation before you put the students in a course like this.
I find it quite interesting how you place a lot of emphasis on almost translating between mathematics and prose. And I can see, well, that's good for things like polynomials, but there are certain words that we use in mathematics that if we bring in the everyday connotations of them, it's well documented students have problems, like limit. The speed limits you can't go past, or you shouldn't go past. Math limits you can go past as much as you want, as long as you limit where you're going, right? Do you broach that with the students? Because no, the emphasis on bringing it back to everyday prose brings with it lots of baggage we don't want. Absolutely.
No. I insist obsessively on, so you think like lawyer. This is what, if, you know, the definition for a mathematician is something beyond question. You have to look at it. And if I define my grandmother is a spaceship, then my grandmother is a spaceship, no question asked. So there is, yeah, I keep telling the students that their inaccuracy of expression, you know, it's quite all right while you're reading the newspaper, but definitions are sacred. So whatever the limit is, it's what's written there.
It just seems, compared to much of the other course, seems to, if I was a student, I might think it was encouraging me to treat symbols like they were words, rather than to have meaning. Because these describe this particular sequence in lots of different ways, suggest that when I see an object that's presented to me like this sequence, I should be doing this internally, and maybe I should be building on the words that I've been asked to use.
Yeah, absolutely.
But these also contain other information that is.
Well, I mean, you know, what words are there? I mean, if I say the coefficient, it's a polynomial. It's a coefficient.
It doesn't have any connotations in real life, yeah. But there's lots of words that do. Limit being one of them.
I never found. I mean, but when I tell the student smooth means smooth, In other words, and I tell them what it means. Smooth means that it has a certain number, apart from the fact that I don't get that level of sophistication, right? But I said, you know, it has a certain number of continuous derivative, which is not, which needs to be specified from the context. So I don't think that the problem is actually the one you describe. I think that the problem is that the students, whether or not that particular term has a counterpart in the common language, their problem is the same. You see, Cartesian product of sets, it doesn't have any, you don't use it in common English. They don't know what it is that either. In other words, there is a comprehensive lack of precision of expression, which is not connected by being distracted by it. Just they don't think like lawyers or like mathematicians. You know, I keep telling them, if you go to a court of law, you have to know exactly what is the distinction between murder and manslaughter. What you and I know is not enough. If you walk in a court of law and you know what you and I know, your opponent will exploit it and make you look totally stupid in front of the judge and the jury instantly. So this is as thinking like a mathematician. So I don't think that the problem you describe is actually, you know, too relevant to this context.
Okay then. Well, last question. Thanks for speaking once again.
Thanks.